Hi everybody, this is Mr. Folly, kind of, and welcome to 3.2. We're going to look at the quantitative aspects of electrons. That means equations. We're going to look at Coulomb's law, and we're going to look at the energy of bond transitions with lights. So let's hop to it. Coulomb's law. Coulomb's law is force equals Q1 times Q2 over R squared. Okay, so F is force. Q is the charges. Notice Q1 now it doesn't have to be specifically 1 is positive and 2 is negative, but notice this force will be negative, and R is the radius. Okay, basically opposite charges Q's attract, but they attract less if they are farther away. Okay, now this is rarely a calculation. It's just an idea. So far away means poor attraction, and bigger opposite charges means greater attraction. Electrons are in energy shells. Okay, these are the words that they're using in AP chemistry now. Energy shells. The amount of energy needed to change shells differs based upon the nuclei because they have different charges, and the distance from the nucleus because that reduces attraction if it's big. The amount of energy to completely leave the atom or ionize it is unique for each atom. C equals lambda nu. C is the speed of light, a constant in meters per second. Wavelength has to be in meters. Now, I'm going to put a little star here, usually given in nanometers. And 1 nanometer equals 1 e negative 9 meters, or 1 meter, which is what I usually do, is 1 e 9 nanometers. Frequency is in 1 over seconds. So when we're talking about a wavelength of something, the wavelength is from crest to crest. The frequency, remember, all electromagnetic radiation moves at the same speed. So if I'm pushing this at the same speed as I'm pushing this one as it moves by would be thump. Oops. Oh no, what did I do? Thump, 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 thump. This guy would be thump, 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 thump. So more energy that way. We can find a wavelength or frequency given the other. So basically, given one of those two, we can find the other one because the speed of light is a constant, which you told me last time was 3e8. Energy of photons used to move electrons, okay, move electrons, we're ionizing them or make them jump energy levels, can be calculated using the above equation. E is the energy in joules. H is Planck's constant in joules seconds. And V is the frequency, and frequency, remember, is 1 over seconds. I don't know why I often use for seconds, and S is the ones used most often. Capital E could be ionization energy and kinetic energy. Okay, kinetic energy can be detected and used for PES, which is photoelectron spectra. PES, we use it a lot. You get used to PES being photoelectron spectra. All right, Schrodinger developed the wave idea and solved wave equations to make predictions about where an electron may be found in the atom. This is the new atom. This is the quantum mechanical model. This, the idea that electrons are waves, along with the uncertainty principle, gives the quantum mechanical model. Okay, this gives the quantum mechanical model the idea that three-dimensional probability maps of where any electron may be found at any point in time within each of these shells. So notice it's a probability. So we're never sure exactly. And that's where the uncertainty principle. Uncertainty principle says the better you know where it is, the worse where it's going, and vice versa. Okay. The idea superseded the simpler version of a fixed orbits provided by Bohr, that's the planetary model, and serves as a classic example of the development of scientific theory based upon new experimental evidence. So it changed. Woo! Look at this. Electrons, I'm a wave, I'm a particle. They're arguing. I'm a wave, I'm a particle. I'm a wave, I'm a and that's true as well. So cartoons make me happy. When is energy given off / absorbed? An electron goes from level 1 to level 4. Notice from 1 to 4, here's the attractive nucleus. If it's going from 1 out to 4, it's breaking a bond. Okay? So if it's breaking a bond, so it gets farther from the nucleus, and a bond is broken, breaking absorbs energy. Whoa, I just misspelled absorbs energy. Okay, breaking absorbs energy. Practice calculations. All right, calculator time. A photon is required to ionize an electron with an energy of blah. What is the wavelength of the light in nanometers? So I'm going to look for an equation that has energy and wavelength in it, and let me go back and look for them. Oh. E equals, wait, no, I don't have that. C equals lambda nu. I guess I got to do that first, huh? Oh man, C equals lambda nu. So 3E8, I hope, equals, what is the wavelength of the light? Oh, I'm not even there. E equals, I used the wrong one. E equals H. Was it lambda? H nu. Let me double check that. E equals H nu. That's it. I am going to use this one, but this one I'm use first. So E equals H nu. So the energy, oh come on, energy is 5.11 E negative 18 equals H, which is a constant, which is 6.626. What is it again? 6.626 E negative 34. Let me look it up. 6.626 E negative 34 times the frequency. Okay, so frequency equals 5.11 E negative 18 divided by 6.626 E negative 34, and I have 7.71 E positive 15 seconds to the negative 1. If I want wavelength, there's that one. 3E8 equals wavelength times 7.71 E15. Wavelength equals 3E8 divided by 7.71 E15, and that would give me 3.89 E negative 8 meters. Now remember, if I want to change that to nanometers, 3.89 E negative 8 meters, 1 meter, 1 E9 nanometers. So that answer times 1 E9, I can't believe I put that in my calculator, is 38.9 nanometers. Okay, yay. An HO bond requires this much energy to break. What is the frequency and wavelength of the photon required? So again, E equals H nu. So 7.11 E negative 19 equals 6.626 E negative 34 times nu. Nu equals 7.11 E negative 19 divided by 6.626 E negative 34, and I have 1.07 E15, and then C equals lambda nu. 3E8 equals lambda 1.07 E15. Lambda equals 3E8 divided by 1.07 E15 is 2.80 E negative 7 meters. Didn't ask for a specific unit, so I'm going to go with that. To review, electrons are in shells. Yay! Coulomb's law tells us the intensity of interaction. You can calculate wavelength, frequency, and energy. Oh, we didn't do that, but I bet you could. Breaking bonds absorbs energy. Ow, I broke a bond. Forming bonds releases energy. Toodles.